Hello everybody, and in this video I'd like to discuss this monster-looking integral. Well, first of all I would like to say that if you're given this integral in an exam or as a homework exercise, I mean, how bad can it be? You can know for sure that it is solvable and expressible in elementary functions. So if you're afraid of monster-looking integrals, don't be, because we'll see that it can actually be solved in a pretty straightforward way. So let's see what we can do here. So this natural logarithm is a nasty function in a way, and we have this complicated expression, but because of the complexity of this integral, it's actually a clue that would simplify our way towards the solution. So the only thing that we can really do here is to make the substitution t equals to whatever is inside the integral. And by the way, this substitution is known as the Euler substitution, because it's an ingenious substitution that is applied not in this case, but in other cases. But it's a nice opportunity to introduce this substitution if you're not familiar with this before. Okay, and so let's see. So obviously we'll turn this natural logarithm to something nice. So let's see what dt would be. And we will see that another miracle happens here. So dt would be, so the derivative of x is obviously 1, and here that's 1 plus x squared to the power of half. So when we compute the derivative of this, we are just going to have simply that, right? And all of it dx. Now note that when we do the common denominator here, what we will have here that this is x and 1 plus x squared divided by 1 over x squared dx, right? And, well, you remember I promised a miracle. Yes, indeed I have, because you see this expression, well, this is t, that we denoted this by t, and therefore we can conclude that dt over t is dx over this square root of 1 plus x squared. Now, how do we proceed from here? So when we make the substitution here, what we get is this is the square root of the natural log of t, right? And then here, the expression, what we have here is that once we substituted this t, then, you know, there's the square root of, this is the x over the square root of 1 plus x squared. So it turns out to be dt over t. That's our integral, right? It's even simpler than that. I wanted to write it as a fraction, but this is it. That's the integral. And now note that the derivative of the natural logarithm of t is 1 over t, right? So if we were to make another substitution, say we will substitute u to be the natural logarithm of t, then du is actually is dt over t, right? So this becomes the integral of the square root of u du, right? Because this is exactly dt over t is du, and this becomes u to the power of 3/2 plus a constant, and of course 2/3, right? Because then when we take the derivative, this cancels the 3/2 with the 2/3 is being cancelled out, and we have the power of half here. So that's okay. And then it only remains to plug in u. But u is the log of t, and then we can plug it all together. And so we would have, our answer would be that this integral equals to 2/3, and then the natural logarithm, which is u, of t, which is x plus the square root of 1 plus x squared, and all of these to the power of 3/2 plus a constant. And this is it. So maybe you would like to discuss another instance where this Euler's substitution is convenient, or where it works. So for example, suppose that we want to compute this integral dx over, say, a squared plus x squared. Then actually the genius of Euler is that he proposed to substitute t as x plus the square root of x squared plus a squared. And then as we computed, dt would be 1 plus x over the square root of x squared plus a squared. This is all the x. And then it all becomes, again, x plus the square root of x squared plus a squared divided by the square root of x squared plus a squared. All of this dx. And again, the miracle and the genius in the Euler substitution is that this is t, right? So this is t, and then again what we have is that this integral becomes, this is just the integral of dt over t. That's exactly the miracle. That's exactly the integral. And so this is the natural logarithm of t, but t is this. So this is just the natural logarithm of x plus the square root of x squared plus a squared and plus a constant. So I promised you one integral, but you got another one for free. So enjoy it, subscribe to my channel, and click the bell button not to miss our weekly integral uploads. Thank you.